Okay, that's fine.
Okay. Well, it's a great honor to be here, and it's especially an honor to be here when you're commemorating a pioneer that I've heard so much about since I've came here and even before. Though I'm impressed by his science and his Hebrew, but I'm even more impressed after I hear you talk, because he apparently gave his children science quizzes at the table and lived to tell the story. And I'm not sure that in my family, if I had tried that with my children, that I would have lived to even tell the tale. So now I'm a really big fan of this guy, because his diplomacy knew no boundaries if he could do that. So it's my first trip to Israel. I'm hoping to see a little bit of your country, and unfortunately, my wife is not with me. She wants to come back, but I've got strict instructions to get a quick look at a few things so that when we come back for our real trip, that she can enjoy it. Today, I'm going to talk about a number of experiments that we've done, and I think they aren't the sort of experiments which typically is associated with your department here. And so I'm going to try and give a bit of a survey rather than go into great depth on any of the experiments. I'm going to cover less than is on the outline, especially since I was told, it's now 20 after, I was told that some fraction of the audience leaves at 5 o'clock, even though I'm supposed to give an hour lecture because of public transportation constraints. So I'm not sure how I'm supposed to do both of those things and survive, but you leave if you have to. So the focus is on the standard model of particle physics. And the standard model of particle physics is something that I think we all in physics should be immensely proud of, and we should all be immensely frustrated with, okay? We should be proud of it because it works, and I'll demonstrate that it works. That we tested its most precise prediction to a part per trillion, and it actually makes a prediction that accurately. And yet it doesn't explain why the universe can exist, okay? And so that's kind of a frustrating big loophole, right? And it doesn't explain dark energy and dark matter, and it doesn't explain inflation. So we know it has to be wrong, and yet where it works, it really works. So that's, I guess that's good because it gives us all job security, right? There's interesting things for us to do, and even for the younger generation to do. So the first part of the talk will be testing the most precise prediction of the standard model. And the second part will be testing standard model extensions, as they're called. These are proposed fixes to the standard model to solve some of the other problems that I just mentioned. Okay, and so we've been able, with the electron, to make some of the very most precise tests of the standard model, and think we can make even more stringent tests in the future. I probably won't have very much time to say stuff here, so in case I don't get to it, I'll just say what's going on here. A number of other experiments that we've done are to test some of the basic symmetries of the standard model, okay? For example, we compared the charge to mass ratio of the antiproton and the proton to 9 parts in 10 to the 11 to see if they're exactly opposite, the same magnitude but an opposite sign of charge. We think we could measure that more precisely now. That same measurement tells us that the antiproton and the proton have the same gravitational interaction at about the part per million level, okay, which is the most precise statement one can make experimentally, I think, about the antimatter gravity. We just recently measured the antiproton and proton magnetic moments, though we made a factor of 680 improvement in precision in the comparison of the antiproton and the proton magnetic moments. One doesn't often get a chance to make steps that big on fundamental quantities, but what's really important is we think we can go another factor of 1,000 or 10,000 as we start to incorporate quantum methods as well into that. And then positron and electron magnetic moments, I'll say that a little bit about that as we go. And some of you know of my work, as was mentioned in the introduction, because my students and I started low energy antiproton and antihydrogen physics many years ago. I should say, for all of the hype about antihydrogen physics, there's not yet any measurements which are scientifically interesting that have been done. Those are still all in the future. And so since I prefer to talk about stuff that's been done, we've made a lot of progress here, but we're not ready to make the really precise laser spectroscopy measurements. So I won't talk about that. Now, what is low energy? Well, low energy is not LHC energy. It's the other end of the thermometer scale. I once made a Scientific American article, and I put the thermometer like this in, and the editor said, but you can't really build a thermometer like that, can you? Well, that's true. Each tick mark is an order of magnitude in energy, right? So there's a lot of energy scale. The remarkable thing is the energy scale that the universe really includes, and this is only part of that. The LHC, which we hear a lot about, is down here. We're doing measurements down in the millivolt region. Okay, and so yet we can make some claims about the Standard Model and its prediction. Okay, the electron magnetic dipole moment. Now, I'm going to be talking about the magnetic dipole moment first, and then the electric dipole moment. For those of you, since there's chemists in the audience, a magnetic dipole moment means it acts like a magnet. Okay, an electric dipole moment means that the charge is distorted, so that there's effectively more charge on one end than the other. And that's what we're looking for. Now, the electron magnetic dipole moment is the most precise prediction of the Standard Model. Okay, there's no other number to my knowledge that the Standard Model can predict more precisely. It's also the most precisely measured property of an elementary particle. Now, that's nice if you have those two things both true, because then it becomes the most precise confrontation of theory and experiment anywhere. Okay, and so that's why it's a really good test of the Standard Model, and the Standard Model survives the test. The theory and the experiment agree at a remarkable precision, and so in a Physics Today article I wrote recently, I actually called it the greatest triumph of the Standard Model. And I wondered what sort of feedback I would get, whether people would be complaining, but no one's complained about that, so it might even be true despite the hyperbole. Now, the electron is an amazing particle, and forgive me for saying really simple things that everyone knows about already, but I think sometimes it's good to reflect on simple things that are remarkable even though we don't choose to think about them so often anymore. I have a lot of electrons in my body, about 10 to the 29 electrons. I'd like to cut that down by an order of magnitude or so, okay, but I have lots of electrons in there. And they give my body its size, as you all know, because the orbits sizes in the atoms are what gives atoms their size and then objects their size. But if you look to see how big the electron itself is, it says, we believe it has no size at all. That means we failed to detect any size. Now, how do you look for size? Well, the most precise way is you take another particle and you smash it into the particle, and you see if any bits come backward, okay? And if nothing does, okay, then you say, well, it doesn't have very much size, right? Because else you'd run into some hard core inside. Now, that's a terrible way to do biology, right? I mean, if you took two chickens and smashed them together and studied the parts, no one would want to do that, okay? But that's how we do it in physics. And we set the limit that the radius, then, of the electron is less than 2 times 10 to the minus 20 meters. In energy units, for those of you who are used to converting back and forth, that's 10 TeV. This is a limit that comes from LEP, from electron-positron scattering. Now, that's a really small size, and this energy scale says that in this half MeV particle, 500,000 electron volts, that if there are ingredients, the binding energy of the ingredients is about 10 TeV to make a half MeV particle. That's a really weird particle if you think about it, right? That's a whale of a lot of binding energy, okay? And so maybe there aren't any ingredients. Maybe it really is a point particle, though to a simple-minded experimenter like me, it's obvious it has to have some size, and I'd love to be the one to find the size. Now, the electron has angular momentum. We call it spin, even though it has no size and nothing is rotating. Now, that's a little strange, right? If you take an angular momentum and you say it's a moment of inertia, a mass times a radius squared, times some rotational frequency, And if the radius is 0 and the rotation frequency is 0, you might actually conclude that the angular momentum was 0. But not in quantum mechanics, because we have this spin degree of freedom. Similarly, for a magnetic moment, that's a current times an area. Well, a current goes as an angular frequency, and an area goes as the radius squared. And if both of those are 0, you'd expect there's no magnet in the electron. But the electron interacts with empty space in such a way to make a magnetic moment. Okay, and so we're sort of used to this sort of thing with the electron, with the magnetic moment. And so we write the magnetic moment as a vector which is proportional to the spin magnetic moment of the electron. Now we do that, there's an assumption here. The assumption is that the electron is really simple. It's not as complicated as a molecule, for example. And so that there only can be one vector in the problem, so all the matrix elements of these vectors, Wigner-Eckhart theorem and all that, have to be proportional. So we write the operators as being proportional. And then we try and measure this signed magnitude of the magnetic moment. And that's the first thing I'll tell you about, the first experiment I'll tell you about. Then the second experiment I'll tell you about, very different technologies, very different approach, but it's asking the same question but for an electric dipole moment. The electric dipole moment, being a vector, had also better be proportional to the spin. If we really believe that it's a spin 1/2 particle that we have, we can scale it like this, and then we try and measure this signed magnitude of the electric dipole moment. So those are the two properties of the electron that I'm going to try and give you at least some idea of how we measure. Now, what is the prediction? The standard model of prediction. I must have been a little too much jet lag when I made that title, okay? This is the prediction of the standard model. Oh, it's my attempt to do Hebrew, right? I guess that's as close as I can get. All right, so the magnetic moment is scaled naturally in Bohr magnetons. That's the charge times charge of the electron times h bar, the fundamental unit of angular momentum, divided by twice the mass of the electron. And so this magnetic moment, which we measure, the standard model predicts it in this form. Now this looks a little complicated, and it is, but let me go through the pieces. The first part is just it comes from the Dirac equation. You all know that if you take the Dirac equation and you go to the non-relativistic limit, what you get is a magnetic moment that comes out, and to a part per thousand, that magnetic moment is the magnetic moment that we measure. Okay, so Dirac did a really good job, but a part per thousand he's wrong by a part per thousand, and that's described by this series here, and this series is the quantum electrodynamics series. That describes the small correction that happens because the electron interacts with the radiation field, or with empty space, which isn't empty because the vacuum is polarized and stuff like this. Now notice here, and I heard it at lunch today too, sometimes people say the magnetic moment is a quantum electrodynamics effect. It's not. Okay? The magnetic moment is mostly just a straight Dirac effect, and the quantum electrodynamics is a part per thousand correction. Okay? And this series, these are all the terms that need to be included in order to approach the experimental precision that we get. This coefficient, or all of these coefficients, get calculated, okay, by some hardworking theorists. And amazingly, these are essentially known exactly, not quite known exactly because you have to put a ratio of lepton masses in, but that doesn't add any uncertainty really. You know, it's a great feat in theoretical physics, I think, that was done. This coefficient, this is the 8th order coefficient, this is the one that my quantum electrodynamics professor in graduate school, it shows how old I am, assured our class could never possibly be calculated. Okay? It's now been calculated numerically, and in addition, C10 just last year was calculated for the first time by Kinoshita and Neo. C10 involves tens of thousands of Feynman diagrams and a lot of cleverness because you have to collapse those Feynman diagrams into a smaller number of, they call them master integrals, that you can actually solve, and then they use every supercomputer on the planet that they can get their hands on to integrate those numerically. Okay, now there's other terms. This is an asymptotic series, which it means it should eventually blow up, but not to worry. We won't lose sleep about that. Okay, then there's a hadronic contribution, a weak contribution, and then perhaps a contribution to due to new physics. Now, here's all of the coefficients as they've been calculated. Here's the hadronic calculation. The weak calculation is actually smaller than what we need to compare experimentally, though I hasten to point out that it's important to be able to calculate that one, because else we wouldn't know it was small enough to neglect it, right? So you have to calculate it. So the role of theorists is very important there as well. Okay. Now, the standard model, notice it's predicting in terms of the fine structure constant. Okay, the fine structure constant is basically gives us the scale of life, right? And so it's an incredibly important constant. Feynman famously said every theorist should put this number 137 on their office wall as a reminder to be humble, because we have no idea how to calculate that number, okay? And yet, you know, everything we know and the scale of life depends on that. So properly speaking, one should say the standard model relates this magnetic moment that we measure, okay, to the fine structure constant, which is in this series here, okay, and the bridge is the standard model theory. Now, for traditional reasons, we tend to put the best fine structure constant we can in on the right-hand side and then call this whole thing the prediction of the standard model. Okay, but the uncertainty when we do that actually comes mostly from the measurement of alpha. Yeah, not from the theory, just to point that out. In fact, the best way, the most precise measure of alpha, the one you see in the front of textbooks, comes from our measurement of the magnetic moment, okay, assuming that the standard model is correct, because that's the most precise way to get it out. Okay, here's just the contributions in that term, because I'm a simple-minded experimenter who needs to see graphs, or else I don't really believe it's right. Okay, this is our Harvard measurement. This is the error bar and the magnetic moment, let's call it 1. And then Dirac said that, well, it should be 1 to a part per thousand. And then here are all of these contributions, and then there's some, I could break it down more. The point is, though, the hadronic correction is important right now, okay, for comparing the theory and the experiment. The weak is not quite important, but if we go another order of magnitude, it will be, okay? So that's where we are. So we have to sample a number of things from the standard model.
What's the dark and the light?
The light here is the full value of the measurement in this case, and the dark just a way of identifying where the uncertainty is. Now, I don't know if you actually know about error bars at this university, right? Because I was looking at the buildings, and you're all from the Faculty of Exact Science, okay? And I felt really embarrassed when I saw that, because I had to admit that I had an error bar, even though it was only 3 parts in 10 to the 13. But I have to admit it. I cannot tell a lie, okay? But that's the difference, right? This is the uncertainty, and this is the effect. Does that answer your question? Okay, and I've preserved that with some of the theoretical uncertainties as well. Now, if you go to CERN and they ask you how big your accelerator is, they don't first understand this picture, okay? Because here's the full team that worked on the last part of the measurement. Though having said that, we worked on this measurement for 20 years. 1 PhD thesis at a time, and after 7 PhD theses, we had enough different new techniques that we put it all together and made the measurement, okay? But this is the big picture of our apparatus. There's a doer here, there's a long skinny apparatus that's out right now, and inside of here, 1 electron will sit for months at a time while we're doing the measurements, okay? And so the actual accelerator is just tens of microns in diameter. Okay, so that's why our budget is so much smaller than the CERN budget, because budgets scale what? As the radius cubed or to the 4th or something like that. Here's all the students that I'm deeply grateful to have worked with, okay? Well, it's 8 theses in the end because Shannon now has her thesis as well, okay? And so these people all made crucial contributions. Here's a picture of the guts of the apparatus. It's something we call a pinning trap, though Pinning never knew what a pinning trap was, okay? Pinning made, did pinning discharges, right? And notice that when you put a magnetic field near your discharge, it lasted longer. And that was because there was an extended orbit that the charged particles went on. I think Hans Stehmelt actually called this a pinning trap first. This is a cutaway of our pinning trap, a little different than those that were used in the past. It's a right circular cylinder inside, even though we want to have an electrostatic quadruple potential that has this form, where Z is the symmetry axis, and X and Y are the axes going out to the side. And what we do is we suspend one electron in here. I blew it up a little bit since it had no size, so you could see it, okay? And then we put various potentials on these different electrodes, and we hold one there. I once held one electron for more than 10 months. Okay, while we were doing experiments. And then one of my colleagues phoned me at home one night and gave me the sad news that the electron had been lost. And my wife still reminds me of this because I was very courteous over the telephone, and then after I hung up, I said something that was somewhat less friendly. And so she still thinks that was showed a personality flaw, and she's right, so. Okay, here's the electrostatic quadruple potential shape that we want inside around our electron. And I don't really have time to tell you about this in much detail, so let me just give you the basic idea. I call this a one-electron quantum cyclotron. Here's the cyclotron like you might build at CERN, only it's kind of expensive to have only one big magnet, right? So you make a bunch of little magnets and you spread them under France and Switzerland and under some mountains and things because it's cheaper to just have a bunch of little magnets. Then you call it a synchrotron because you turn it on and off, but the principle is the same. For an electron, in a 6 Tesla field, the particle would orbit at about 150 gigahertz. Now that's a 2 millimeter microwave frequency. It's really tricky to work at that frequency, but I won't have time. I'd love to give you whole lectures on just how we do that, but we don't have much time. Okay, now as I drew it, there's a problem with this apparatus. Namely, if there's any net charge anywhere, the electron will go up along the field line and go right out of the apparatus. And we take a long time to do experiments. Remember, it took us 20 years? Okay, so we can't let the electron go away. And so what we do is we put negative charges above and below. Okay, and so when the particle goes up, it says, whoops, I see some negative charge, don't want to go that way, because these charges repel each other, and it's stuck in between. That's the basic idea of the pinning trap. Now there's a little more to it, and those electrodes I showed you are actually what we bias, okay? But this is the basic idea. Now, CERN is already doing a fine job at this, and so what we want is not that. We want to cool it down so much that only certain radii are possible, only certain energy levels are possible. And if we cool it down enough, what we're going to see is these essentially equally spaced energy levels. Okay, and in fact, we do the experiment essentially in the ground state. There's the wave function squared of the ground state. It's a really boring accelerator, right? Because nothing goes around in a circle. It just sits there in a spherically symmetric way, in a cylindrically symmetric way. And then we go up to the first excited state. That's almost as boring a state, right? We have a name for these boring states. We call them stationary states because nothing happens, okay? So at CERN, at the LHC, there aren't too many people who worry about which quantum level, you know, their proton is in, right? For us, the whole experiment is in being in these two low levels, okay? And we do all of the experiment that way. For example, if I'm in the ground state, okay, and then I put in some microwaves, okay, at 150 gigahertz, then I can make a transition from the ground state to the first excited state. Okay, and then I count, I say, well, how many times does that happen per applications of this microwave drive? And then I change the frequency, and then I measure it again. And that's how I can tell what frequency is the resonant frequency. Okay, now in order to do this, to get this in a low temperature, you might want to think about that. What do I mean by temperature? The temperature of one particle. If you think about this, where's the ensemble hiding? Okay? Basically, the ensemble is I do one measurement on this electron, and then I do another one, so I divide the time sequences up into slices, and then if I average all of those time sequences together, then I get the ensemble average for I can describe with a temperature. But normally I can't describe it with the temperature. It's either going to be in the ground state or the first excited state, provided that I'm in thermal equilibrium at some temperature way lower than the temperature that corresponds to this energy difference. Okay, so I have to cool the apparatus down way below 7 Kelvin, so I actually cool it down to about 1/10 of a Kelvin using a dilution refrigerator. Okay, and then the particle sits in the ground state essentially forever until we put photons in the cavity to boost it up. Now, here's the math that you have to do. Okay, the energy levels for this quantum cyclotron, there's the n plus 1/2. This is the quantum number for the cyclotron motion, so that should be a familiar harmonic oscillator expression. And then the electron has a spin, so there can be spin up or spin down. So ms can be 1/2 or minus 1/2. It's the spin quantum number. And now if I put these two together, this spin h bar omega s and h bar omega c, I could write these in terms of the Bohr magneton and this constant as I've defined it, and the result is that just what I want, the magnetic moment in Bohr magnetons, is given by a ratio of two frequencies that I can measure, by measuring which frequency of drive most efficiently excites cyclotron excitation, one quantum at a time, and which frequency of drive flips the spin. Okay? Now, there's nothing in physics that we can measure more accurately than a frequency, except the ratio of frequencies. Okay? Because a frequency, the timekeeping is so well developed that people are making clocks that are good to parts and 10 to the 17, over a very long range of time scales. A ratio of frequencies is even better because now your clock only has to be stable between the time you measure the spin frequency and when you measure the cyclotron frequency, which is a much more relaxed assumption. So you can measure this very accurately. Now you have to be careful, and there's a number of things that I won't have time to talk to you about. Okay, but for example, every time I excite up one quantum level in this cyclotron excitation, I get a relativistic shift. Okay, because the cyclotron frequency isn't EB over m, as most of you think. It's EB over gamma m, where gamma is the relativistic factor. Now, that gamma for us is 1.000000001. Most people would say that's really non-relativistic, okay? And it is, but our precision is so high that we see a shift, all right, a part in 10 to the 9 per quantum level, which is significantly bigger than the precision at which we measure things. Okay? All right, so here are the energy levels of this one electron bound in our apparatus. The way to think of this is we're really making an atom. We're making a homemade atom. It's different than a proton because it's less tightly bound. That means when we measure the properties of this atom, we can really learn about the properties of the unbound electron in a way that you can't in a proton and not in a hydrogen atom as easily. Okay? All right, so here's the transitions we drive. We start in this state, we drive it up to here. We start in this state and drive to here, in which case it decays spontaneously down to the lower state. I don't have time to explain this, but this is the sort of signal we see to signal that we've done a one quantum transition. For those of you who do or know some quantum optics, these are quantum non-demolition measurements. Okay, and I just don't have time, even though I'd love to talk about that. But this is a spin flip. Okay, you see, you can't miss the fact that the spin has flipped. Okay, this is the ground state, and this is going to the first excited state of the cyclotron motion. Okay, so again, we can read this out very, very clearly. We have to do some tricks. I could spend a couple of hours talking about all the tricks. Okay, but let me just give you one. We inhibit spontaneous emission. Okay, Now, in a cyclotron motion, you know this, for you accelerator people know that synchrotron radiation is a big problem in something like LEP. You make a big ring or else all the synchrotron radiation is going to melt the beam pipe, okay, because there's so much radiation that comes out. Okay, well, we get synchrotron radiation even though we're in the non-relativistic limit. Gamma cubed is pretty close to 1 when gamma is essentially 1, okay? But it's still our predominant decay mechanism, our only one, in fact, that we know of. And if we take these quantum jumps that we observe and just make a histogram of how long the particle stays in the first excited state, then we see this nice kind of decay at 16 seconds. If you calculate what this should be, it's about 1/10 of a second. Okay, and you can use, quantum radiation theory or classical radiation theory. They give the same answer. But what's different is this trap cavity that we put around the electron. I showed you a cutaway picture of that. We carefully chose the dimensions of that so that it makes a cavity. Now, you know when you calculate the density of states, right, for calculating a transition, you start with some cavity and then you let it go to infinity. Well, experimenters can't make apparatus that goes to infinity, right? So we have small things. So then we still have a density of states that's lumpy. So if we arrange that the cyclotron frequency is not close to one of the radiation modes of this cavity, the particle looks out and says, boy, I'd really like to radiate today, but guess what? There's no density of states, and so it can't radiate. And that's important, this trick, not only because it's nifty, but because it gives us the averaging time that we need so that we can average long enough to see that it's only one electron and which quantum state it's in. So those are the sorts of things one has to do. Anyway, that's all I have time to talk about for this measurement. Here's the result that we had. After 20 years, we made a measurement to a rather ridiculous precision, okay, of 2.8 parts in 10 to the 13, okay, which was a rather substantial improvement on the measurement that Hans Steinmetz won the Nobel Prize from many years ago. Okay. Now, if you say, again, back to my hyperbole, the standard model's greatest triumph, here's the predicted value that comes from the standard model. And that idea is just to compare these digits. And by George, they agreed to a part per trillion, okay? That's a remarkably good prediction that the standard model is able to make, even though the prediction was finished after we finished the measurement, right, because they had to calculate the 10th order in order to do this. Here's our measurement again, and here's the prediction of the standard model. And again, the error bar on here comes from the method used to measure the fine structure constant independently, something that I don't really have time to talk about, but it uses atom interferometry. One of the founders of quantum electrodynamics sent me this lovely note after we made our measurement. And he said, as one of the inventors of QED, I remember that we thought of QED in 1949 as a temporary and jerry-built structure with mathematical inconsistencies, and we normalized infinities swept under the rug. We did not expect it to last more than 10 years before some more solidly built theory would replace it. And he said, it's amazing that we can measure this dance to a part per trillion and find her still following our beat.
The part from the hadronic part you take from experiment?
No, that's calculated. Well, this is not strong interaction physics. It's vacuum polarization involving hadrons. No, it's calculated is my understanding, and there's an uncertainty that's given with it. It's just the lowest order drawing diagrams. I can get you the references if. Yeah. Well, we can discuss it more after if you'd like, but that's my understanding.
You could take it from experiment, of course.
Well, perhaps, but I believe that's not how it's done. But we can look at the reference together. Okay. Now we could test for physics beyond the standard model because the good agreement between theory and experiment doesn't leave room for an addition due to new physics. Okay, now some of you know about the muon g-value measurement that's being done, And the muon measurement is important even though it's about 2,500 times less precise than ours, because this factor is expected to be 40,000 times bigger for the muon than for the electron. It's heavier, and there's a much stronger interaction as a result. The problem with the muon experiment is that this hadronic term and the weak term as well, but they're 40,000 times bigger as well. Okay, and that means it's very difficult to calculate that accurately, and there the calculations are a lot, taking experimental structure functions and stuff like this and integrating those. Okay, and right now, as you probably know, there's a 3 sigma difference between the prediction and the measurement for the muon magnetic moment. Okay, and that's either something that's very exciting because it's the first sign that the standard model is breaking down, or it's a problem with this term, in my view. Okay, but that everybody has different opinions about that. Okay, I think I won't say anything about the other. I'd like to get on to the electron electric dipole moment measurement. This is the most precise test of extensions to the standard model, and it's 12 times more precise than previous measurements. We just published it recently at the beginning of this year. And again, I've already explained this. What we're looking to see is the charge squished in the electron. So even though the electron has no size, is its charge squished inside of the no size, so to speak? And is there an electric dipole moment? Now, the answer was obviously no for some generations of physicists, right? Because basically, if you do a parity transformation on a system that has an electric and a magnetic dipole moment, you get the 2 moments pointing the opposite directions. And these can't both be true, okay, unless one of them is 0. We know that the magnetic moment, mu, is not 0, so the electric dipole moment would have to be 0 if parity was a good symmetry. Of course, it turned out parity is not a good symmetry, so now what about this one? Well, if you do a time reversal transformation, you again reverse the order, the direction of the 2 moments. And so if time reversal were a good symmetry of reality, then also D would be 0. So for many years, people didn't look. And Purcell and Norman Ramsey, Norman was they were both my colleagues at Harvard. I was fortunate enough to take the slot that Norman vacated when he retired. But they pointed out that this was based on, I won't read it now, but it was based on theoretical assumptions, namely the assumptions that I just went through, and that in the end we should look, okay? We don't just trust our theoretical assumptions too much. And when I was a graduate student, Norman showed this lovely graph in a seminar that I heard him give. And for those of you who didn't know Norman Ramsey, he's a big guy with flaming white hair and a booming voice and boundless enthusiasm. He really, you know, if anyone actually seemed like a messiah, that would be him, okay? And he'd measured the neutron electric dipole moment for many years. And what he did is he gave every theorist a box, okay, to make a prediction of their favorite model, and not to bias things. He didn't put their name on, just a letter. And then he would calmly reduce the size of the magnetic moment, because he never did find it, to his great frustration in all of his years of looking. And he said then that all these boxes would then disappear when he made the measurement. And he said, but there was this funny thing that happened. They would reappear sometimes back on the other side. And that's when I first learned about fine-tuning. Okay, you adjust some parameter in your theory to make it work after all. But anyway, I was inspired to go into this sort of physics. The standard model says, well, there is an electric dipole moment of the electron, but it's about 10 to the minus 38 electron charges times centimeters. That's just an arbitrary kind of unit because there's no real natural unit for it. The reason that that's a pretty small number is the best measurement when we started in this business about 5-6 years ago was 10 to the minus 27 centimeters.
For the electron?
Electron, okay? That's remarkably different, right? So even an optimist like me with good graduate students willing to work 20 years on an experiment doesn't think you can go that many orders of magnitude so easily, okay? So here's the explanation for that, but most of you understand this better than I do. You have to go to 4th order perturbation theory to get the CP violation that we know about, okay, and so on. That's the story. Now, what's different, the standard model then has all the low-order diagrams, they vanish. What's different about almost all the extensions to the standard model is their lowest order diagrams don't vanish. So they naturally predict a much larger electric dipole moment. Okay? So it's a wonderful place to try and distinguish between the standard model predictions and these extensions, to look at the standard model, at the electric dipole moment. So we put three groups together, which is a little unusual in my field. We usually don't have money to do this, but John Doyle's group at Harvard, my group at Harvard, and Dave DeMille's group at Yale, we decided to do this all together, okay, and see if we could do it on a somewhat more rapid time scale than is usual. Okay, and in fact we managed to do that in 5 years. Now here's the old guys looking as wise as we can and hiding our potbellies, okay, but down here are the people who did all the work, okay, and we had really excellent students, which was a nice thing. So what could one expect to do? Well, here's all the theories that we know of, and you can't tie the theorists down to a specific prediction, because there's things like masses of particles we haven't discovered yet, and phases which describe how much CP violation is involved, okay? And so, but if you do the best job you can, naive supersymmetry, as it was called, is essentially ruled out by the best limit that was already available before our ACME collaboration started. But you can see almost all the theorists are sitting on the wrong side of the line, right? Which means either we should be able to detect the electric dipole moment if we can measure in here somewhere, because there's a lot of different theories predicting a non-zero value, or we should be able to rule out those models. Okay, and our first goal was to make an order of magnitude or so improvement, and I'll tell you about how well we did. Now, first let me say, how do you measure an electric dipole moment? Well, the idea is the Hamiltonian for an electric dipole is the dipole interacts with the electric field, okay, D dot E. That means if you believe that D is really small, which is why no one's discovered it yet, you want to make E really big, okay, and then you can make an energy shift that you can hope to detect. So it's as simple as that, the basic principle. A big E so that you can measure a small d. Now, of course, putting a big E on a big electric field when there's an electron around is a bit of a problem, right? Because you put the electric field on and it blows it right out of the apparatus and your experiment's over. Okay, so electron EDMs are done with atoms and molecules, and we have to then cope with the fact that life is a little more complicated. Schiff almost killed the whole business. He pointed out that in non-relativistic quantum mechanics and that limit, that basically what would happen if the electron in an atom or a molecule had an electric dipole moment, the charge distribution around would just rearrange so that you'd be invisible. That would be invisible and you couldn't tell what was going on, okay? That was a downer. But then Sanders in 1965 said, well, if you're relativistic, things are really better. If you take an atom or a molecule and have a really heavy nucleus, the electron goes whipping around near that nucleus. There's a time dilation factor, and that time dilation factor essentially gives you a big enhancement in the effective size of the electric field. So his contribution was really critical, and here's an intuitive explanation of that. So we decided to use a molecule. Now, I must say, I hate molecules. With apologies to the chemists, I just admire you folks who have enough brain cells so you can understand molecules. They just don't have much symmetry. You got to memorize everything. The states are A, B, C, D, E, and X and stuff like that. There's just no symmetry principles there. But what you can't argue with is they have an incredibly large electric field inside. Okay, and so even if you don't like molecules, you kind of hold your hose and you do it, because if you take the atom, the best atom before that was used to give an EDM limit, the effective electric field inside was 72 megavolts per centimeter. Now a megavolt per centimeter is good, but our molecule has almost 100 gigavolts per centimeter. Okay, a gigavolt is a lot bigger than a megavolt, right? And you just can't possibly make something like that in your lab. So, okay, molecules, here we come. Which molecules are the best? Here's a paper which laid out some of the possibilities. Ed Heinz group at Imperial College used YBF and made a measurement that I'll refer to shortly. Okay, and we're using THO, and there's some other groups that have tried some other molecules, but no results at this point. Okay, now I won't go into the molecular physics, but our molecule has a lot of nice features, okay? The most important of which probably is that there are two opposite parity levels which are essentially degenerate, okay? That means that we can, with a very small electric field, we can fully saturate, you know, the mixing of those two levels. And that means we get the maximum electric field by applying a laboratory field of only a volt per centimeter or so. Okay, now even I can control a volt per centimeter, right? But to take a volt per centimeter and control a gigavolt per centimeter, that's really something. Okay. The other thing is this molecule. Here's the levels these two levels here that we use. Okay, each of these shifts when you put a magnetic or electric field on due to magnetic and electric dipole moments. But the other nice thing is instead of using these two levels, we can use these two levels. And to do that, we just excite with a laser, where we either excite these two states or we change the frequency and we excite these two states. That change, without changing the external value of the fields at all, allows us to change the internal value of the field without the external field, which is really important for suppressing systematic effects. Okay, so that's just one of the things we do. Now, the EDM still only gives a tiny shift of energy levels. Since a lot of you are particle physicists here, I put it in units you can understand. The splitting is 7 times 10 to the minus 30 TeV. Okay, that's not so many TeV. If you're an atomic physicist or a chemist and you do it in EV instead, I have no idea what it is in kilocalories or something like that, but it's 7 times 10 to the minus 18 electron volts. So it's not a very big shift. You can't resolve it by sweeping a laser through, okay, and resolving these two levels. Nothing will resolve this. So what's the basic idea of how do you detect this? Well, you use an interference experiment. You have to make a quantum state, which is a superposition of two states, but it's a coherent superposition, meaning there's a definite phase relationship between the wave function of these two states. Okay, and then you let it evolve in your electric and magnetic fields, whatever it is that's causing this splitting. And now the two states evolve differently because they have a different energy, right? The evolution goes as e to the minus I over h bar times the energy times time, and you have two different energies. It's the difference of these two energy levels. And in fact, the phase then is this energy splitting we're looking for times the time, which you make as long as you can to exaggerate this effect. So it's kind of a quantum amplifier, so to speak. Right, and then there's an h bar in there. So we have about a 1 millisecond coherence time. That's how far we let it evolve. It's about 11 microkelvin. Okay, that's the limit that we got for our first measurement. This is my building at Harvard. The lasers are all in my laser lab, and there's 100 meters away, 2 stories underground, is where the molecular beam is. So we have lots of optical fibers going back and forth between these two labs so that we can connect them to do the experiment. Here's just the scale of the experiment. This is a table which isn't so different. It's just a really tiny laser table. Inside here we make our molecules. That's a specialty of the Doyle group. Okay, at Harvard, you take a really intense laser, you go splot into some thorium dioxide, and stuff happens, as they say, right? You get this big discharge, and who knows what's going on. And out comes some thorium monoxide, THO, a molecule. Okay, and my hat's off to people who can understand what goes on in such an ablation. We let cold neon gas collide with these molecules and slow them down. So coming out of this blue box, they have about a temperature of 4 Kelvin. They come down the path here. Okay, and then inside of this vacuum chamber, there's the parallel plates that make an electric field. Okay, and that electric field is the one that we reverse to change the direction of the energy shifts of these two energy levels. There's mu metal all around and stuff like this. Here's the basic idea of the experiment. Here come the molecules between the field plates. We can put on a parallel electric field if we want. We make the coherent superposition with one laser, and we detect it with another laser system. Actually, there's lots of other laser systems, but I'm just going to simplify from here on out. Okay, so what happens with this measurement then? Well, let me switch here to some results. Well, before I get to the results, let me just show you this. There's a phase difference which depends on the electric field and the electric dipole moment. If we switch the electric field dimension, the direction, then that phase changes. This is this phase we're evolving. That's basically the signal we're looking at. We're also switching other things. We're switching the magnetic field. We're also switching the electric field internally by switching our laser excitation. And then there's a bunch of other things we do. We're able to turn these on and off in seconds, to tens of seconds. So we're doing all these reversals and then subtracting off, you know, when the phase going in the opposite direction. So we're normalizing in place all of the time. We see lots of data that looks like this. Most of it looks just like noise, and this is a phase that corresponds to one particular set of sign symmetries. You know, how it, one particular term.
What do you really measure?
Phase.
Where is the electron in the molecule?
We understand that the electric field comes from the molecule.
Yes.
And where is the electron which sits in this electric field?
The electric moves around in this electric field.
Where do you put it in? Where it comes?
We have to rely on molecular theorists to give us one theoretical number, which is the average value of the electric field that the valence electron sees.
I would like to phrase the same question. Do you measure the dipole moment of the electron or of the molecule?
Of the electron.
Well, we measure a phase difference, which, is there a board here? Okay, now I'm not going to get done for sure, but where's, do you have a, we're measuring a phase, which involves a lot of terms, including D times E effective. Okay? Now, I need to get this from a theorist, what the size of that electric field is. And this then it comes in fact from the electron. This is just the term now that's coming from the electron itself, from the intrinsic dipole moment of the electron. The molecule is polarized. It has a big electric field as well, but that's a separate thing. Okay? Maybe we should talk about it afterwards, because else I have trouble.
Let's continue with the talk.
Okay. And so I'm sorry if I'm not explaining it clearly enough. I apologize. But anyway, we're measuring this phase, or actually small changes in phase, that correspond, for example, to changing the direction of this field, which we can do in two ways. We can change this field by changing the volt per centimeter, actually 100 volt per centimeter field that we apply in the lab, okay, or we can change it by changing the internal direction of the field. We'll do it for one direction and the other and subtract the two, and that change of phase is exactly what we measure. Okay? And then we can deduce the size of the electron EDM only if a theorist gives us the value of this effective electric field, averaged over all the orbitals that it occupies in the molecule. Okay, so we see these sorts of effects, and in the end then we're able to set a limit on the electric dipole moment, okay, from converting phase now to phase to, using this effective electric field. And we got, our result was consistent with 0, which was disappointing. We did the whole experiment blind, so we wouldn't know what the answer would be. And at some point when we had decided we were ready to publish whatever the answer was, then we removed the blind, and it was consistent with 0, so then we made it to a limit. At the 90% confidence level, it's less than 8.7 times 10 to the minus 29 e centimeters. Okay, now that's a factor of 12 lower than what we had before. And then it came out on the cover of Science, and I'm very disappointed by that because I was proud that in my whole career I had never ever submitted a paper to either Science or Nature. Okay, I called them hype journals, and I wasn't going to publish there. Okay, but my two colleagues outvoted me, and so it ended up going to Science, so I have to apologize for where we put this. Okay, in terms of the particle physics result, okay, this is just to show you that we're at the LHC time scale, energy scale. The electric dipole moment divided by electron charges is the weak interaction scale times the loop of the diagram. This is where CP violation comes into the problem. Okay, and there's a sign of a CP violating phase that comes in. You can make the simplest assumption that that's about 1 because no one has a good argument as to why that phase should be small. Okay, and when you put these two things together at the n equals 1 or n equals 2 loop diagrams, well, and we put a prefactor in just to be conservative. We didn't want anybody from the LHC sending us letter bombs or anything. Okay, so we said maybe it's 10 times smaller because of a prefactor. Then we're in the 3 TeV for 1 loop diagrams or 1 TeV for 2 loop diagrams, which is roughly the energy scale that the LHC is probing these models right now. I can show you a table from Atlas, and I'll be quitting shortly. Okay, this is the Atlas table, and you can see if you could read all of these, hundreds of GeV up to a TeV is sort of the energy scale that's mostly being probed there. Okay, I'm gonna quit now, and basically I could go on, but well, let me end with this. It's good to end with a fairy tale, right? If you take the level of, you could say, how sensitive is our princess? You maybe have heard this old fairy tale. The princess was so sensitive that life would be hard, but she could feel this pea under all of her mattresses. So how big is the pea here? Well, it's a little hard to scale up an electron to any reasonable size since the electron has no size, right? But you have to do something. So you can take the classical electron radius, which is the size of the polarization cloud around the electron, right, the vacuum polarization. So classical electron radius is a really bad term, right? I mean, it's not classical in any way I can imagine. But okay, if we scale that to the size of the Earth, then the dipole moment limit that we set corresponds in terms of mass moments here of shifting the Earth center by 2 nanometers, okay? So it's fairly sensitive. So I apologize that I haven't explained this as clearly as I would like to, and that's a serious thing. But what I did want to do is give you a flavor, if I could, of what sort of things can be done at low energy if you have enough tenacity and good enough students, okay? And so it is possible to actually make some small contribution to particle physics even in 2014. Thanks.
Thank you very much for the beautiful talk. You know, movies sometimes end with a statement, don't try this at home. But maybe you can try it at home. So we have time for a few short questions. Yes, Naftali?
Yes, this limit of about 10 to the minus 28, that I think is, for a dipole moment, has been achieved more or less in the Mercury 199 experiment for as a dipole moment of Mercury 199.
Yes, that's right. That's right.
And
it's quite
the same kind of put down some of the theories already that you have shown.
Yeah,
So that's about the same, even maybe slightly better.
No. Well, that's it depends on how you look at it. Let me see if I can find the slide. I skipped a bunch of stuff because I was going slower here than I wanted to. I don't see it right now, so let me just describe it in words, because what you say is not quite right. Part of what you say is right, namely that if you look at the Mercury electric dipole moment itself, it's comparably small, okay? But what one is usually focuses on is from that limit, what sort of limit can you set on the electron, proton, and neutron electric dipole moments? And none of those can be set nearly as precisely. Okay? Now, having said that, I think it's very important not only to measure the electron dipole moment, which we measure much more precisely than the other two, but it's important to measure the others as well, because there are very different ways that CP violation can enter the problem in those other systems, because there's the strong interaction inside the, and so,
I agree with that.
yeah.
Of course, but as a limit of a dipole moment, any dipole moment, of a molecule, of a electron or proton, whatever, neutron, it's comparable to this result.
Well, yeah, but that's not the point, right? I mean, if I make the really accurate measurement between my nose and your nose and measure it to a bunch of significant figures and no one cares, I mean, what we have to do is decide, and this is, I'm not trying to make fun of this, in precision measurements like this, one of the hardest things sometimes is knowing what it is that you should measure. What are the interesting quantities? Okay, and I would say that the electric dipole moment of an atom itself is not an interesting quantity. It's not of any interest at all in terms of fundamental physics.
Very interesting, because it tells you something about time reversal. So
Okay, we can.
Okay, well, at least we have a difference of opinion.
Sarah?
So, yeah.
I would be very grateful if you would go back to your slide that showed all the different theories and where they were going to be tested.
Yes?
This number on that slide.
Yeah, I skipped that at the end here. So, that's what happens when people start going to the door. I just stop. So, this was the limit. This was the limit that I showed you before we started. Okay, we have now put these theories, shall we say, require some fine tuning. Okay? And there's a number of them that we have not yet been able to rule out or discover the EDM from.
It's really a model-dependent statement, right? I mean, you need the small phase, and it's not fine-tuned to you to come up with a small phase. CP phase, I mean, these new models. You can come up with symmetry principles for why you.
But if you pick a small phase for no reason, isn't that fine-tuning?
Well, it's not fine-tuning in the way, it's quantum mechanically natural. In that sense, it's technically natural. The proof would call it technically natural. But also, I mean, I'm saying that there are symmetry principles, CP violation in that case sector, that would shift all these models towards, far away from your line. We don't see why that's expected.
Well,
The simplest theories don't produce that, but if you are forcing us to do it, we'll get it.
well, no, but no, but with all due respect, I think that if we don't have a good reason to pick, a CP violating phase, which is 10 to the minus 4, then I don't see why we would expect to find such a thing.
I'm not disagreeing. I'm saying you can write models where naturally these CP phases are.
But naturally means I want a small one so that I don't disagree with the.
Reason for why they are small.
But that's what everybody's doing here. Okay. So split supersymmetry, for example, is deliberately putting two different mass scales that are widely spaced just to suppress the size of the EDM that's produced. Okay, but
There are two different. There's the scaling of lambda. And there's the
I
scaling
think
of-
we are getting into
Okay.
a level of discussion which is beyond the colloquium. So one last question.
I've given this talk at Fermilab and at CERN in front of many theorists, and no one has ever quibbled on this point before. So it'll be interesting to discuss it later. So yeah.
How big an electric dipole moment you need to measure to accommodate the observed symmetry in matter? This is your motivation.
Well, okay, let me say this. I don't know the answer, okay? But, and I would say that's not the way I think of it, okay? I think it's embarrassing that we don't have a good answer to why the universe could possibly exist. And what that means, though, as a first step, is that we should look and see if we can find some symmetries that are broken that we didn't think should be, or that there's some symmetry violations where we didn't realize they were before. And
It means that this measurement will not, no matter what limit you will...
no, I didn't say that. No. If we find an EDM limit, I promise you, I absolutely promise you, that within a month there will be 100 papers on the archive with explanations, okay, and there'll be...
So long you think it will be?
Yeah, well, you know what I'm saying? No, look, we have to make one step at a time, and until we actually find an unexpected symmetry violation, then it's a hard job to make a whole model. So I don't concede that it's irrelevant at all. I just have to say I don't know, okay, and be honest about it. But if I waited to make a measurement until I had a full model, I mean, jeepers, then I'd be waiting for theorists. I don't do that. So, yeah.
Okay, thank you very much again.